Good morning, ladies and gentlemen. I'm pleased to see such a crowded room for the next 60 minutes where I'm going to talk about C# 7, some language enhancements that came with the latest version of Visual Studio 2017. And the next 60 minutes I will not present any slides. That's important. I will do 100% demos. I will not write a lot of code, but I will walk you through some code. But what's more important for me is that I don't want to just show you the new syntax variants. I mean, you can Google that and you can read articles on the Microsoft documentation and things like that. I want to spend the majority of this session in more detailed tools that allow us to take a look behind the scenes. And for instance, take a look at what the new language features means performance-wise. How does it perform? What is the IL code that is generated from these new syntax constructs look like? How does it differ from the way you wrote C# in the past? This is what I want to do in the next 60 minutes. My name is Rainer Stropik. I come from Austria. I have a small company there. We are mainly doing SaaS development based on Azure, and our entire backend is written in C#. So C# is one of my favorite languages besides TypeScript and Python, and therefore I'm really looking forward to the next 60 minutes. Let's jump right into the first demo. What you see here is my Visual Studio 2017 preview. I've installed the latest preview and we'll give it a try. I hope it will be stable enough. And we will start slow. We will start simple by introducing a new feature that you might have already heard about. It's called expression-bodied members. I guess you have used expression-bodied members before with C# 6, but now with C# 7 you have new possibilities of expressing your functions and properties and constructors and finalizers in an expression-bodied way. Take a look at that one here. This is a new feature from C# 7. It expresses the C# constructor with an expression body. Or take a look at that one. The property. You can express, in that case, the setter in an expression-bodied way. You are essentially writing a kind of lambda expression and you're saving some typings. I mean, you save some angle brackets and some return statements. Well, is it a revolutionary new functionality? Well, no, it isn't. But it is some kind of syntactic sugar that makes your code more compact and hopefully more easy to read. If we combine these expression-bodied functions, even with a new feature that is also new here in C# 7, the so-called throw expressions, it's getting even more interesting. If you take a look, for instance, at that one here, this method, setEvenNumber, wants to set the member even number to a parameter, but only if this parameter is an even number. So what we can do is we can use an inline if here and use, now new in C# 7, the throw statement as part of the expression. So we don't need to write this if statement with the throw in a separate line or in multiple separate lines. We can write it in a more compact way. We can write a single liner that hopefully expresses better our intent, what we intend to do. The question is, how does that look like if we take a look behind the scenes? What does the compiler do with it? And it's just a warm-up example. It will be nothing revolutionary new, but I would like to use this example to introduce you to a tool that I'm going to use throughout this session. It's called dnSpy. dnSpy allows you to take a look at the generated IL code, or you can even generate your C# code out of the IL code again. But dnSpy can do a lot of things more. You could even change the code inside of the assemblies. We'll not use this feature during this talk, but still it is a very nice tool to take a look at what the C# compiler does with our expression-bodied members. Let me zoom in a little bit. So I think you can read that one. And let's open up on the left-hand side the expression-bodied members. Let's at first take a look here with C# on the constructor. It's the constructor of this type here. And if you can remember, we had this expression-bodied constructor here. And as you can see here, the C# compiler just adds some syntactic sugar. It's nothing new. The code is exactly as we would have written without the expression-bodied member. Nothing special here. It's getting more interesting if we take a look at this combination from this expression-bodied member together with the throw expression. So let's take a look at this set_not_null string method. If we take a look at that one, then we'll see that the C# compiler generates behind the scenes exactly the same code that you would have written without this throw expression and without the expression-bodied members. So, what is your takeaway from this first sample? Expression-bodied members got better in C#7, first. Second, new feature, throw expression. It's very useful to write more compact code, but behind the scenes, well, nothing changed. The compiler is just offering us some syntactic sugar, some things that make it easier to write good, readable code. So with that sample, I wanted to introduce you mainly to the dnSpy tool, because now we are shifting gears and we are going to take a look at something very new and something revolutionary new that really changes some fundamental things in how we might write code. I'm talking about local function. How did you write local functions in the past? Let me show you this code here. Let's zoom in a little bit. Make it more easy for you to follow. Let's take a look at this basic local function. It's really a basic function. I know it's very simple, but well, simple is sometimes good to understand the basics and the very concepts. What you see here is I'm using a delegate with a lambda expression to define a local function, let's call it function, which is called add, and then I'm using this local function built on top of a delegate inside a console write-line statement. Nothing new. I'm quite sure that nearly all people here in the audience have written code like that. In that case, the method add is really a local functionality. It's not exposed to anybody else. It's just inside the scope of the enclosing method, which is called basic local function. You might wonder, why the hell would somebody do that? I mean, I can write a private function inside the class, can't I? Well, if you write a private method inside of your class, you're exposing this code to anybody, to an entire class. And maybe this functionality, this add functionality here, is something that only makes sense in the context of basic local function. Maybe it needs access to local variables. We see that here with the closure example. You see, here we have a local variable called random value, and we are using this variable random value inside of this other add implementation. So imagine you have a lot of this state. You don't want to pass it around. You just want to use it inside of your local function. Maybe this local function needs some specific initialization code that is just done inside of your enclosing method, in that case the closure method. So it doesn't make sense to offer it as a private member, because somebody else who is also working on your class might think, hey, this method comes in handy, let's call it, and forget that it just doesn't make sense in a more generic context. It only makes sense in that context. So we've written that code. That's nothing new. But now we can really write it differently. It looks very similar, but behaves in the background very differently. Here you see the new version of basic local function. Please note line 26. Here you see again the add functionality, but this time it's not a delegate anymore. You see? I'm still using the expression-bodied syntax here, but it's not a delegate. It's really a native C# local function, which is called add, and I can use it in line 27. The functionality, on the other hand, is very, very similar. It just works in a similar way than the delegate. We can also take a look at the more complex function here, the closure, and you can see inside of this add local function, we can still access the local variables which are in the scope of the enclosing method. So you can do essentially the same as you did with your delegates in the past. But what I am really interested in is what's happening behind the scene. Is it faster? Has it become better? Well, Let's take a look. Let's first take a look at the old version. I'm going in dnSpy and I'm going to open the release compiled version of the old syntax. In that case, it's a .NET Core application, so I'm using .NET Core 1.1 here, and I'm going to open the basic local function. Let's switch to intermediate language here, and here is the basic local function. Yeah, this is the basic local function. Awesome. Let's move it like that, and yep, this is exactly what I want to show you. What you see here is especially that one. Oops, I didn't want to click, just that one. Please note the new object here, the IL code in line 20. What it does in that line is it's allocating a delegate on the heap. So by using the local function, we're really putting pressure on the garbage collector. If we do that, for instance, in a tight loop, the garbage collector has a lot to do, because with every local function, with every declaration of the local function, it's creating a delegate on the heap. And the second thing what I want to show you in the old world is this call vert in line 29. It's a virtual function call, calling this local function that was defined using a delegate is really a virtual function call. And as we all know, virtual function calls are more expensive than normal function calls. So what we want to do, what we want to achieve, is we want to get rid of this new object and we want to get rid of the call virtual. And we want to check whether the new functionality of C# is really achieving that. Let's take a look. I'm going to open the new version. By the way, at the end of the talk, I will show you where you can get these sources. I have written a blog post where you can reread all the things that I show you here during the talk. So if you want to take a look at it at home, it's no problem. Basic local function. I mean, just by looking at this code, we immediately see that it's much, much shorter. There is no new object anymore. What we see here is that the local function here has become, I can click on it, has become a plain static function, and it's just called. You see, we have a plain call here in line 20. Is it 20? No, 12, sorry. So no new object, no call vert. It really makes a huge difference if you define it with the new native local functionality of C#7 instead of using delegates. It is a huge difference. But to make one thing clear, if you just use a single local function and inside of the enclosing function you do things like database calls or web APIs, your I/O will probably be so slow that it doesn't make any difference if you do a call vert or a call and if you do another new object or not. It makes a difference though if you are running inside of a tight loop, and I will show you that with Purview in just a few minutes to really prove the point that it makes a difference. It's just a few percentage and it's just in some edge cases, but still if you are in that edge case, you will probably be happy that it works like that. Let's take a look at the closure function. Let's take a look at the closure here. Please remember, the code of the closure function, let me quickly go here, looked something like that. We were defining a local function which is called add, and we were accessing the random value, which is a local variable in the scope of the enclosing function, of the closure function. And the difference is just that in the new version we're not using a delegate anymore. So let's take a look at what happens here if we take a look first again on the old version. What you see here is that we are again using a new object. Here we can find it. Here you see the new object here, but we will even find another new object up here. What you see here in line 14 is that the C# compiler in the past created a class consisting of the add function plus the random value local value to put them together, to bind them together, close together, a closure. And if we take a look at this class, it's called display class. We see it here on the left-hand side. You will see that this is really a class. And this class consists of, let me zoom in a little bit, it consists of the function, this is the local add function, and the random value. So these two things are bound together. This is how using a local function, a closure, in C# worked for many years. So we have additional overhead if we are going to use closures with local functions based on delegates, because we are essentially not having any stack-based memory here. We are really allocating another class, so we are giving the garbage collector even more to do. How does that look like in the new world? If we take a look at closure, we will see here at the very top of the method in line 10 that we still have a thing here which is called display class, but don't let you fool by the name. It's called a class, but it isn't a class anymore. If we take a look at that one, and here you see the display class 4, let me zoom in a little bit, it has another value, it has another different color here. It's green. Can you see that on the video beamer? Yes, you can see it. If I click on it, you will see that this now is a struct, it's a value type. So the new functionality does no longer create the display class. Well, it creates something which is called display class, but essentially it's a struct. And this struct does, as you can see here, just contain the random value. And if we take a look what's happening with the local function, let me go back here, then we see that the method, where is it? Let me look it up. The result is, here is my closure. Here it is. That now the add method, the local add method, is rewritten by the compiler, so it does no longer just get x and y as input parameters, but it receives the value type that has been created by the compiler in the backend as another parameter via the stack. So there is no need for a new object on the heap. We have less to do for the garbage collector, and again, if you execute this code in a tight loop, for instance, that really makes a difference. Because, yeah, you are using less memory and the garbage collector is happy. Okay? Let's take a look at what that really means in terms of performance. I've done the following. I've created a small algorithm here. Well, it doesn't make any sense, but I wrote it to just make the point. Let's first take a look at the old version here, many calculations. Let's zoom in a little bit. Yeah, something like that. As you can see here, I'm doing a very simple loop. I'm just looping until for 10 seconds. So for 10 seconds, I'm doing nothing else than this one. And please note line 88. That's the important thing. The other thing around is just for measuring, just for demo purposes, okay? In line 88, you see that we're using a local function add, but this time in a tight loop. So for 10 seconds, we're using a lot of local functions here. And in the new version, I'm doing exactly the same code, but this time with the native local functions. So let's try this. Let me open up the new version here in File Explorer. Yes, here it is, and go to bin. Oh no, let's start with the old version. Let's go into Lambda and bin and release and netcore and let's copy this path, and then let's run our friend Perfview. If you don't know this tool, Perfview, take a look at it. It's really awesome. Let me quickly remove old collections and select run. And as this, let me zoom in a little bit. As this is a .NET Core application, I cannot just select any executable because currently I don't have an executable. So I will use the .NET runtime to spin up my DLL, and I can do some basic things, give it a little bit more memory, and that's fine. And then we let this thing running. So what this thing currently does, it's executing our code in the background. It's running for approximately 10 seconds, and in the background, it's gathering some performance measurements. Let me see. Yes, it already sent the rundown command to the compiler. Yes, oh, it was very fast. So this was the 10 seconds. Our tight loop executed our local function for 10 seconds. And if we take a look at the garbage collector statistics and look for, where is it? .NET, here it is, .NET. And if I zoom in a little bit, you will see something that is really astonishing. We have in 10 seconds 2,800 garbage collector runs in Gen 0. That's a lot. Why do we have this 2,800 garbage collector runs? Well, because of the new objects. Is that placing a huge penalty on our performance? Well, not really. It's just a few percentages overall. If you're doing even some I/O code and things like that, it's maybe only a very small fraction of your performance. So you have to use a profiler like Purview or Visual Studio Profiler to really take a look in your concrete situation if it really makes a difference. But it can, in some situations, make a difference. And to be honest, the new syntax is so easy to use. Why not using it always? And even if the performance advantage is just small, benefit from it. So let's prove the point and go to the new version here. A local function bin and release and net core app, and let's copy the path again, and let's go close that one and go here. Delete the Purview stuff and click run again, and this time we are using .NET with a local function version. And again, we have to wait for another 10 seconds, and hopefully we will see a difference. Well, I expect that we will see a difference. Let me see. It should be done in just a few seconds. Yeah, here we are. It's already loading it up. Let's go to the memory group, let's go to GC stats, and let's go to .NET local function, and this is exactly what I want to see. 0 garbage collectors. So we just saved 2,800 garbage collector runs in that sample by just switching from old delegates to new local functions. That really makes a difference in some use cases. So, what is the takeaway of this sample, of this new feature here in C#7? The takeaway is that using local functions or preferring local functions over delegates is really worthwhile. You should do it always. There are no drawbacks that I'm aware of. You can do all the nice things that you are used to with delegates, but now you can do it natively in C#7 and you will get slightly better performance. But again, please remember, don't believe anything that somebody on stage tells you about performance. Always use your own profiler on your own code with your own representative test environment to make sure that it really is a benefit in your concrete situations. Always measure before optimizing performance. Okay. Next one. Let's take a small one before we dive into the next huge change in C#7. The next one here is the outvar feature. The outvar feature isn't very revolutionary. You see here I have written some lines of code. Here you see the classic code. I'm declaring a number here, and I'm using try parse, and I'm just using an out parameter. Nothing special. It's really, really simple. And if we take a look at the new version, the C#7 version, we can now write outvar. So we don't need to declare the variable outside of the try parse statement. We can do it directly within the function call. It declares a local variable called number, and this local variable can be used now. It makes a bit of a difference if you combine it with another neat functionality. Take a look at that one here. In that case, I have written a method which is called return some numbers. It returns 3 out variables. And imagine in a situation like that, You're just interested in the first value. You're calling this return sum and some numbers, but you are not interested in value 2 and value 3. You can now use the underscore here to indicate that you are not interested in this return value. Okay? This is a nice feature that is coming with C#7, and you can use it in various situations. Whenever you call something, or you get, for instance, we'll see later on, you get a tuple back from a method and you just want to have parts of it, you can use the underscore to tell C# that you're not interested in these parameters. Of course, you could do it something like that, and the question is, does it make a difference? Does it make a difference if you use _var and if you use the underscore in terms of performance and in terms of code? Let's take a look. We don't believe anything, we test. Okay, let's go back to dnSpy and open up our _vars sample. Let me close that one, close that one. Here is the _vars, here is the _vars, here is the _vars, open that one. And if we compare the classic version with the C#7 version, let me zoom out a little bit. It doesn't really make any difference. You probably can't read the details here. It doesn't make any difference. You can try this example at home if you don't believe me, but just by looking at the structure of the code, you see that the generated IL code is absolutely identical. It doesn't make any difference. So this feature, the _var feature and this underscore feature, is again just like with the first feature that I showed you, the expression bodied functions, it's just syntactic sugar. It makes your code more compact and hopefully more easy to read. You can express your intention better with the new features, but performance-wise and IL-wise, it's the same code that is spit out by the compiler. Okay, this one was to rest a little bit before we go into more details. Now we're diving into another major feature of C#7, and it's called pattern matching. Before we take a look at more details and the IL code that is generated from pattern matching, I want to introduce various syntax variants of pattern matching to you. I want to start by taking a look at these two functions that I've written for you. Take a look at line 23. 23 defines a local method which is called checkClassic, and what it does, it receives an input parameter of type object, and inside of the method it checks whether object is a string, and if it is a string, it does something with this string. In line 33, you see the same code, but this time we've done something very new, with something brand new that has not been there in previous versions of C#7 and of C#. What you see here is an is pattern. A pattern that says when object is of type string, then assign the value of object to the local variable name. The scope of local variable name is the same scope as shown here in the checkClassic. So name is a local variable inside of check C#7. You could not declare down here another variable called name because it would be a name conflict. You would use the name twice, and that's not allowed. However, the C# compiler makes sure that you don't access name outside of the if. So if I do something like, for instance, name.length or something like that, we are not allowed to do that. You have seen that IntelliSense has given me the method length, so it knows about the variable length, but it's not allowed to use it because it's not safe to access it, because maybe the value hasn't been assigned. Well, not maybe, the value definitely has not been assigned outside of the if statement here. However, I can easily move this one up and everything will be fine because we are inside of the if statement, and in that case the is pattern has been true and the value of and name has a value. we can take a look at how this looks like in Roslyn if we take a look at the syntax tree. What I'm using here is the C#, the Roslyn syntax visualizer. You can get it if you install the Roslyn tools. And if we take a look here, if we click on it, we can zoom in a little bit, and then we see the classic structure, the classic syntax tree of a C# if statement. Here you see the if statement. I will go something like that so you can follow along on the right-hand side. It's just an if statement, and inside of this if statement we have a binary expression because we are comparing with a binary operator, not equal. And here we have the not equals expression, which is a specialization of the binary expression. This is the guy that we know and love for many, many years now. Now let's take a look at the C# syntax tree with the C#7 version. And here we see again the if statement, but inside here we get something very new. This is no longer a binary expression. This is a new part of the Roslyn syntax tree. It is the so-called is pattern expression. Okay, so this is something that has been has been brought completely new to C#, and therefore we have nothing to compare. It's not like the other things where I can show you old version and new version and the same IL is spit out. This is something entirely new. Okay, you know what? Let's take a look at the IL. Because of course we want to know what happens behind the scene. Is it similar to what C# did in the past, or is it completely different? Let's open up the pattern matching here, and let's zoom in a little bit. Here I have the program, yeah, and here I have check classic and that one, and let's again zoom in a little bit. Maybe let's take that one. I hope you can read it. Is it okay? Yeah, I think so. At the top, at the very top, we see the classic version. What we see here is we are using the IL instruction is instance, and then we are popping the value from the stack and storing it again on the stack. These two, it looks like that. Okay, this is the IL. And if we scroll down a little bit, we see that the code looks very similar, but not entirely similar. Microsoft has changed the generated IL code a little bit. So you probably ask, well, is it faster? Is it equally fast? Well, I don't have statistics for all the different operating systems and CPUs and ahead of time compiler and just in time compiler. I don't have this entire statistics. I probably think that Microsoft did it, but I was curious, and before this session I ran some tight loops over these implementations on my machine here, Windows 10 and all this stuff, and .NET Core 1.1, and the new implementation was approximately 2 to 2.5% faster. Again, it doesn't make a very much difference if you have a lot of I/O and other algorithms go on, but if you are in a tight loop, it could maybe make a difference. But nevertheless, independent of whether you want to save or enhance your performance, I think the syntax is much better. You can express your intent much better. Okay. You can use that one in ifs, but of course, pattern matching knows has more tricks than that. This is something that is much more practical. In that case, take a look what I do here. I have a list on the right-hand side, and by the way, this is a new feature of C# 7.2. What you see here, you can use a separator if you have very long numbers, so you can use that with decimal numbers. You also get now binary numbers in C#, and you can separate them here too. And you can use here, you can use it in hex numbers too. So a nice feature, but I think we don't have to spend much time on it. The important thing here is that, remember, I have a list, but I assign it on the left-hand side to a variable of type IEnumerable of int. Imagine that I now pass these numbers here to a subroutine that expects IList, but inside of this subroutine, there is some code where the implementer can do special optimizations in case that the that the collection that it's given supports, for instance, indexing, whether it supports, for instance, iList. So imagine you have a function where you can say, hey, if it is an iList, if this IEnumerable guy is an iList, I can do something very special with it. And if it's not an iList, if it's just an enumerable, I have to do the hard work, for instance. Then you can again use, here you see it, the is pattern by checking whether the IEnumerable that you have been given implement a specialized interface like iList, and therefore you can do something very special. So this is, I think, a very practical and good use of this is pattern. Of course, we can do the same with our own classes. If we have polymorphism and if we have a dog which derives from animal, this works perfectly fine. Let's take a look at the switch statement, because this guy, again, is very interesting. What you see here is I'm switching on a local variable which is called O, and O is an object. So O doesn't have a specific type. Well, what can we do? First, let's start here. We can use a very similar syntax than with the is expression inside the if statement. We can say, hey, if this O is a string, then assign the value of O as a string to object name, and we can immediately access the object name, okay? You probably have guessed that one from the if statement example. That one is a special form of this down here. In that case, we are expressing, hey, if this O is a string and if its value is foo, then we want to do something special. So you can combine is pattern with the constant pattern. In the if statement, you would say, if O is foo. You can do that too, but you can do it right here in the switch statement. The C# compiler is even very smart. If we try to do that one, the C# compiler will say, nope, that doesn't make a sense, because line 72 will never be reached. Why will line 72 never be reached? Because now, and this is an important takeaway from this session, the order of the case statement really makes a difference. And I want to show it to you in a few minutes inside of the IL code. In that case, the first case block in line 68 is reached because O is already a string, and then the case block in line 72 cannot be reached anymore because the first one already does the trick. Okay. Here you see another possibility, which is new in C#7 in combination with the pattern matching. The first part of this case block in line 77 is something that we now already know. It's just to check whether O is a double. And if it is a double, we assign its value to the local variable called number. But what we can do is we can add another guard here. We can add a when statement, similar to some try-catch stuff that is also new, but I will not cover it in that session. The when guard here checks that the number has to be greater than 100. And this is the very nice thing here. And of course, in that case, you can combine multiple of these case statements, and we will go into a more detailed example in a few more moments. Yeah, of course, you can check for null, and you can even write something like case var object. Well, I'm not really sure when I would use this feature, but still it is there. So essentially what it does, it's always true. Okay, so it just assigns O to object, and you can do exactly the same. You could also write a default expression. Okay, nothing special. Cool. Let's take a look at this example and take a closer look behind the scenes, because today we really want to look behind the scenes. What I've done here is I've created a switch pattern. In that case, my example does something similar than before. What I do is I assign the value 42 as a double to an object, and then I'm doing two case with an is expression, with the is pattern, sorry, with a guard. And in that case, the guard says if D is greater 10, and in that case, if D is greater 20. You can express that in C#. It's perfectly fine code, it's allowed. But in our situation, the object O has the value 42, so this would be true for both case blocks. What does the compiler do? The first question I ask is, does it do the type checking 2 times? Or does it optimize the type checking so the type checking is only done once for both case blocks? That's the first question that I want to ask. And the second question that I ask is, how does the IL code look like? Can I see inside the IL code that the order of the case blocks really make a difference? And this is what we are going to look at here in dnSpy. Let's look at the pattern matching. Oh, I already opened up the pattern matching. Yeah, switch with pattern demo. I think this is the method. Yeah, switch with pattern demo. Yeah. Okay. We don't have to go through all the details here in this code, but what we see here is we have our good friend isInst here again. So if we take a look at the IL code, we see that we can immediately answer the first question that I expressed. The type check is only done once inside of the IL. And the other thing that we see is, if we take a look down here, where we have the check whether the value is lower than 10, we see that the method here, once it reaches the end of the first case block, just to make sure we are here now, yeah? So this is the statement here. It's immediately returning from the function. So it's not passing on the control to the second case block. It cannot happen that 2 case blocks are executed because it's immediately returning from the function. That's the point. So what is the takeaway from this example? What should you take away from this code? First one, the C# optimizer is smart if you are using pattern matching with switch. It only it combines multiple type checks and executes them only once, so that's an optimization. And the second thing is, make sure that your case blocks are in the right order, so otherwise maybe you have an unexpected behavior. Sometimes, as you've seen up here, the C# compiler is smart and it can disallow that you combine the case statements in a certain way where it can definitely say that the code you write doesn't make sense, but in some cases it allows case blocks that could both be true, but yeah, the order makes the difference. Okay. Next one. The next thing I want to show you is tuples. And I just want to make it very clear, I will not go through all the very details and syntax variants of tuples. You have lots and lots of blog posts and documents in docs.microsoft.com where you can take a look at all different syntax variants of tuples. Yeah, I have my sample code online too. If we wouldn't have 1 hour, if we would have 2 hours, we could go through all the different things with my sample here. I just want to concentrate on the very basics. I want to show you how tuples work behind the scene, and well, by the way, if we see some interesting syntax, we'll talk about it, but my intention is not to show you the entire functionality of tuples. Let's take a look first at the classic, maybe I shouldn't call it old, the classic syntax. I'm not old, I'm classic. You see, this one is a typical version of an algorithm that, for instance, in that case, uses an array of numbers and it wants to return 2 results. It wants to return sum and it wants to return count. Well, one thing that you could do is you could just use out parameters. Out parameters, as we have already seen, have become, well, more convenient with the out var feature. But still, it's not perfectly nice syntax. We want to do something else. Well, a good friend that we know for long now is the tuple of t, or in that case, tuple of t1 and t2. In that case, we're just doing the sum and the count, and we are returning the tuple of int and int. Nothing special. We know this stuff for quite a while. We can access the items, the members of the tuple with item 1 and item 2, and that's the problem. Okay, that's the problem that the new tuple system of C#7 wants to solve. I mean, this is an invitation for programming errors, for programming mistakes. Because if you have longer code and if you declare the tuple here and 5 pages of screen pages down below you access item 1 or item 2 and simply you cannot remember was the sum in item 1 or item 2 and bad things happen. So, what we want to have is we want to be able to assign the different items with a name. And that's essentially what the new tuple syntax does. It allows you to return, as you can see here, it allows you to return a tuple in the, by using these parentheses here. See that one? On the left-hand side, we can declare a local variable which consists of 2 items. Behind the scenes, this is just a tuple, but it's a very special tuple. Let's take a look at the IL. Let's take a look at the tuple demo and release, and here it is, and let's go into the tuple demo. Here it is, and let's open it up, and we are looking for the main method. Here it is, here it is, here it is, okay. Okay. You immediately see what's happening by taking a look at the local variables. What the C# compiler does behind the scenes, it's just using a new friend of our class tuple. It's called value tuple, and as the name suggests, the new friend is no longer a class, a reference type, but it's a value type. So it's very, very efficient. If you just combine some integers or other value types, you have now a value type for the tuple. So everything is going on the stack. You are not placing a lot of pressure on the garbage collector by allocating a lot of memory on the heap. That's the whole point of introducing the value tuple. If we take a look, let me see if I find that here on stage. Here I call this one analyze. Where is it? I think it's that one. And this method here, yeah, here you can see it. This method, which internally does the sum and the count, returns an instance of value tuple. So what we see here is just syntactic sugar, which is very similar to what we have written here. However, the C# compiler will internally no longer use tuple of T1 and T2, but down here it's going to use value tuple. This guy here, these two things are called semantic names that the C# compiler is able to give the items of the value tuple. So the C# compiler allows you to rename item 1, item 2, and so on, assign a name to it, and with that, write cleaner code and make less mistakes. Here you see just a few possibilities. You see if you assign this value to this tuple here, you can access the items just by using the semantic name. So if I type dot, I get nice IntelliSense here, but still, take a look at that one, still we see that behind the scenes it's just value tuple. So we can still use item 1. You shouldn't, but you can. That's the point. It's just value type. And you can do a lot of things. Yeah? You can just say var, you don't need the type here, and you can do lots and lots of things. You can do deconstruction. Please take a look at the endless number of blogs that you find out in the internet. I don't want to repeat that. I think that's boring. We just want to concentrate on the things that are going on behind the scenes. The question that I want to analyze further is with this method here, with this analyze method. I think it has become clear that the C# compiler knows that it has to generate some IL code using value tuple, and if it takes a look at the C# code, it of course knows the name, the semantic name of the items of value tuple. But what happens if you take this analyze function and put it inside a DLL? And if you ship that DLL to your customer, there is no source code, there is no C# source code where the Roslyn compiler could peek into and take a look at it and says, hey, I know this guy is called sum and this guy is called count. We don't see that one, okay? So somehow these semantic names here have to survive inside of a class library. Because technically in a class library, if you just take a look at the IL code, the return type is value tuple. Full stop. It's not sum and count, it's value tuple. And if you use it, you would just see item 1 and item 2. So what happens behind the scenes? Let's take a look here at our analyze function. And yep, here it is. Let me zoom a little bit. What we see here is we see, compiler services, compiler generated attribute. What we see here is that the compiler adds a new attribute on top of your method that is returning the tuple. And this attribute is called tuple element names. So it's just assigning metadata to your method, and the C# compiler, Visual Studio, will look into this metadata, it will respect the attribute, and is able to give you IntelliSense for sum and count. Well, where are the names? Somewhere hidden here, you see? Let's copy these hex values and let's inspect them. Hex to text, I'm sure there is, yeah. I'd take anything here, and let's convert it, hex numbers to text. And if I zoom in a little bit, we see a lot of unprintable characters, but still we see sum and count. So the binary stuff inside of this compiler generated attribute contains the semantic names of our two items inside of value tuple, and this is how the semantic names survive compiling a method that returns a tuple in a class library. Because Visual Studio will take a look inside of this compiler-generated attribute, and with that, it can give you IntelliSense. Okay? That's going on behind the scenes. A nice thing that is worth mentioning before we go on is the deconstruction stuff. The deconstruction stuff is shown here in line 64. In this line, you see that I'm using the parentheses on the left-hand side with the var here, and the important difference compared to that guy here is that this is the method declaration, okay? This is calling the method. The important difference is that this is no longer a tuple, but what we do here is we declare two new local variables called mySum and myCount. It's no longer a value tuple. We are deconstructing the value tuple that was returned by our analyze method, and we put item 1 into the local variable mySum and item 2 into the local variable myCount. There are different alternative syntax. Choose the one you like. So this one is nice because you can again use the new underscore to indicate that you are not interested in a certain part of this value tuple. So if you take a look at line 72, you see that there is an underscore, so we are just interested in the sum, we are not interested in the count here. You want to know how the IL looks and what the C# compiler does behind the scenes? I will not do that on stage because I only have 60 minutes. That's homework for you if you like. Give dnSpy a try and use the sample to explore it. Okay. These deconstruction thing can now, and that's new, can now also be added to your custom classes. I will not go into the details here, but just to make one thing very clear, this has generated some confusion in trainings that I do, because people know that there is something like a destructor or finalizer, and now we don't only have a destructor, but we also have a deconstructor. So what you can do is you can create a method which is called deconstruct, and this deconstruct takes the internal state of the class, assigns some out variable, and if you have this method which is called deconstruct, you can write something like that to rip your, in this case, point apart, take some pieces out of the point and assign it immediately to local variables. Sometimes that comes in handy. I don't think that it's revolutionary new, and I don't think that you will use it every day, but I wanted to mention it in this talk. Okay. Last but not least, we have 5 minutes left. That's perfectly fine. I want to spend the last few minutes with a new guy, which is called value task. Here you see it. I'm quite sure that everybody is familiar with task and task of T, TPL. Don't we love it? TPL is great. It's even greater if you add a little bit of async await. The problem with TPL and task is that it's a reference type. And in some cases, reference type, as we have seen before, are a little bit of an overhead. If you are creating a lot of task instances, you are creating a lot of objects on the heap, and if you create a lot of objects on the heap that are short-lived, you are placing some pressure, you're putting some pressure on the garbage collector. We have shown you, we have seen that in this talk by using Purview, and it's the same here with task. If you have a situation where you, for instance, do some I/O or read some data from a database, but in some cases you have this data already available in memory, in a cache, for instance, then you typically write code like that. You say, is it in cache? If it is in cache, we just use task.from result. And if it is not in cache, we are using an async function behind the scene to do some I/O, for instance. And we're just returning the task. The problem is here with this task.from result. Why do we have to return a task here? Because the user of our function getResultTask without await wants to be able to use await. So the user of our functionality wants to be able to do something like that. Await, okay? Await with something that returns tasks. In the past, C# did not allow you to use async await with anything else than task, and this has now changed. As long as your method, as your class contains something that is called a getAwaiter function, so as long as it returns something which is called an awaiter, please take a look at the in the Microsoft documentation to learn more about this thing. As long as you have this method, you can await it. And what Microsoft did is they now allow us to create a flavor of a task which is no longer a reference type but a value type. You see it down here. This is essentially the same code as you've seen before, but this time we are returning a value task, and this is a struct. So if it is in cache, we can just create an instance of this value task. It's not on the heap, it's just on the stack. And if not, we can surround the task that we get from our async method with a value task to have a nice method signature that always returns a value task. And if we compare these two things, if I run this guy, you will see that the version with the task and the version with the value task, I'm using a tight loop again here to do some testing, the value task version is a little bit faster. But now comes a word of warning. I've seen many developers seeing this value task thing and immediately thinking of, wow, we have to refactor our entire class library. Let's use value task always and throw away task. That's not a good idea. In many, many situations, I would even say in most situations, task outperforms value task. Take a look at my source code. I will show you the GitHub address in just a few seconds. Take a look at my source code. Play through all of the different flavors of this get result stuff here, and you will see that most of the scenarios task is faster than value task. So what I'm telling you is, use a profiler. Use a profiler like Purview. Do, for instance, garbage collector analysis as I've shown you in this session at the beginning. And if you see that you really have a garbage collector problem, that your performance problems are related to memory, then try value task. Then you have a new tool in your tool belt that is probably right for your specific situation. But it's not a silver bullet. So please don't go home and change all your tasks to value tasks. That's the important takeaway from that last sample. And with that, we have 24 seconds left. If you Google my name, as I said, my name is Rainer Stropek. Or if you just remember our dev blog address, software-architects.com/devblog, you will find an in-depth article that I wrote yesterday night in my hotel room. I summarized all the different things that I've shown you. I added a lot of screenshots, so you can replay all the samples that I've shown you. You can follow the links to get my source code from GitHub. You can follow the links to download the tools. It's always a two-sided sword with doing sessions without slides. I can't hand you out slides, but this session is recorded, and I try to give you as much material as possible by summarizing this thing in this blog post. I hope you like the material. Thank you very much for coming to this session. I hope something you have learned, something new. Everybody has found something valuable in this past 60 minutes. And I wish you a very nice Techorama for the rest of the day. Thank you for coming.